Welcome, welcome. AP Physics C is going to start with this video. This is the beginning video for the course. We're going to be in the unit of kinematics, but going over the basics, some vocabulary definitions, and some of the notational things you're going to see throughout the year, but focusing on Unit 1, kinematics in particular. So this video is going to focus on two major things. Representations, big focus of AP Physics C, so we'll see what College Board has to say about it, and then kind of simplify it to what we're going to be using more specifically in Unit 1. We're also going to look at scalars and vectors. This is a pre-calculus topic, but we'll make sure we define it, look at some examples of how we're going to use it here in Unit 1, and how we can use them in equations and diagrams. So from here, let's take a look at representations first. So what is a representation? According to College Board, you can read along with me here. The various modes for describing, organizing, communicating aspects of motion and interactions. I did make up that definition, but that's essentially what College Board is saying, and then the rest of this is actually from College Board's mouth themselves. These are examples that they use in all of AP Physics C. Again, we're going to focus on what they're going to use in Unit 1 here to narrow it. The reason why they're doing this is that your ability to understand something is going to be predicated on your ability to communicate that same idea across these different modes of communication. So if you can only tell me what it is, but you can't draw a picture, you don't really know it well enough, right? Or if you can't graph it, or you can't do algebra or calculus with it. So it just diversifies what knowledge is, especially in physics here. So let's look now at Unit 1. So put simply, what are we going to do? We're going to be looking at the narratives. We're going to be diagramming or sketching a motion or interaction. We'll look at how tables are involved, graphs, and equations or math. Okay, so what are each of these different representations going to be, or how are they going to take form? Narratives, for example, are just going to be like your written problem. Okay, so they're going to describe the motion in words, or text in this case. So something can move with the direction, like forward or backward, left or right, up or down. Right? We can just say those things. We're going to be looking for those words to assess the directions that something is moving, right? Or getting pushed, etc. Something from a motion standpoint can be speeding up. It can be slowing down. And it can do those at either an even rate, or it can be speeding up at a increasing rate. Same thing for slowing down. And it also can just have constant motion. The other thing we can make sure we understand is there dimensions that are involved? Like, is it just a straight line that's moving along, or is there a straight line but also left and right, meaning like a two-dimensional plane, kind of like the floor in a room, right? Or something turning along a circular path. That would be another example of a two-dimensional plane where you're making like an arc of a circle as you go. If we diagram stuff, you can see these different examples of diagrams here. We're going to be labeling out different information that we can measure or that we're given, and we can talk about where something is in like kind of a point A to point B. It's a list of information, but it creates the context in a visual way instead of just simply listing them, like in a table, for example. So diagrams are very powerful for establishing a length or spatial dimension. And they're great for connecting this point to this point. Maybe we start here and make a third part. So they're going to be great for multiple part problems and just really complicated situations where we want to list out what we have given, but not lose the context, not lose the problem. We can see them in action. Tables are going to be typically what we get from data collection, but they can come in multiple choice or free response, where the College Board problem is giving you data that you essentially collected, because you can't actually collect data on the AP exam. We can also do what's called a motion map. Now, I listed this in the table category, although College Board would say this is its own thing. But you can see here, this is where some object is. If I were to draw a dot representing where it is each second, so 0, 1 second, 2 second, 3 second, 4 second, etc. as it moves, then I can see that it's going to be increasing the speed that it is able to travel each second until some point around the middle where it starts to get a shrinked distance each second. So this would tell me that it's speeding up and slowing down. So in the same way a table lists an actual numerical value at each second, this is showing a visual or a diagram at each second. So I'd probably combine these tables and motion maps to be in the same category. You can see here, this is just showing a ball being thrown up in the air. So you can see on the way up, it's getting a lesser speed or distance in between each point, and then on the way back down, it's going to be increasing that distance and speed as it descends. Okay, let's move on to graphs. There are two types of graphs that we're going to deal with a lot. This is a huge focus of AP. We're going to be sketching or interpreting qualitative graphs, which are just showing us the qualities, no numbers. This would be an example of a qualitative graph. You see here there's no numbers. It's just focusing on that shape. Same thing with this one over here on the right. Just focusing on this shape, which is the relationship that's at the focus of this problem. As soon as we throw numbers on these axes, changes the game entirely, and we call those quantitative graphs because they have quantities that are actually on those axes. And you can see this middle one is an example of a quantitative graph. And lastly, we have the equations or math. So these are some scary looking ones here. I can put some calculus on here, so you may not know what this is actually saying, but these would be examples of what we'd have on our equation sheet, and these are ways we can just mathematically solve for things. We can derive equations, but we will not just be focusing on math alone. This is just one of many other representations, so we're going to treat it as such. Now the notation that we're going to deal with here, we're going to get a deeper dive into when we get into scalars and vectors for our next part. So without further ado, we're going to look at now scalars and vectors. Okay, so these always give people the cringy heebie-jeebies here. So scalar and vectors are just two categories for any variable. So if I give you a variable like t equals 3 seconds, t, which stands for time, has to be either a scalar or a vector. So a scalar is going to be any quantity, such as time, that is fully described by a number value alone. And the number value we're going to refer to as a fancy math word, magnitude. Okay, so magnitude is when you just talk about a number value. Like, how tall are you? I'm 6 foot tall. Magnitude is 6. Okay? Or how much time has gone by? 30 seconds. So the magnitude is 30 seconds. How fast are you going? I'm currently going 25 miles per hour in a car. I'm not doing that right now. I'm sitting at a desk, but the magnitude would be 25 miles per hour. So you can see here a bunch of different examples of quantities that don't have a direction to it. They're just simply a number value. How much time? How far did I go? How fast am I going? How much mass do I have? You can also think like pounds kind of too here if you don't get into the force unit just yet. Energy, rotational inertia, we don't know what that is, but these are examples of things we're going to deal with in AP Physics C that are magnitudes and do not have a direction. If we write them in math, we're just going to list them. There's not really anything to do. You just write the letter variable, and you just know that that quantity is a scalar. Now, if this is a vector, I'm going to come back to this, then we can talk about the magnitude of a vector. So I'm going to come back to this bottom part here in a moment. So let's go over to the right side. Now, vectors. Vectors, I just think of as being arrows, just so you know. Like, I just think of, like, if someone says vector, I immediately visually see in my head an arrow. Okay? And these quantities that are vectors are variables that are described fully when you have both its magnitude, again, just a number value, but also then a direction. So we can't just have a number value. I can't just say that it's 25 miles per hour. I have to say it's 25 miles per hour forward, or 25 miles per hour backward, or left, or right, etc. So these variables, these number values, have a direction associated with them. So a vector has to have two pieces of information always. Its magnitude, which would kind of be like the length of the arrow. I always think longer is stronger. So if we draw visually a vector as an arrow, then a longer arrow would indicate that it's a bigger magnitude. And then obviously the way it's pointing would indicate its direction. So instead of distance, if we care about the direction you're going, like I need to go east or west or something, then we call that displacement. And the speed, if we actually need to go forward, backward, left, right, etc., then it would be called velocity, not speed. Acceleration is a speeding up or slowing down. Force is a push or pull that has a direction that you can push or pull, momentum, torque, and we'll keep going through the rest of these as we go through the year. So how do you write a vector? You do just write the letter variable, but to indicate that we're talking about a vector here, you put a little arrow over it, and that indicates it's a vector. And if we have that, then we're going to have to show both the number value, right, its magnitude, and its direction. And one way we can indicate the direction that we often use is to let the answer be positive or negative, which would indicate the direction. If I'm going forward, positive. If I'm going backward, negative. So going back now to our scalar stuff, if I do have one of these vector variables that have an arrow over it, and I write them as an absolute value, then that's saying, hey, this variable does have a direction to it, but I'm only really focusing on its number value right now. And so that's why we would say absolute value, because you're not worrying about that negative sign, which would normally indicate that that's going backward. So you can see here, if you have some distance that's along the x and y axis, then how far you go, which would be distance, would be the magnitude of the resultant vector, right? Which is going to be like the Pythagorean theorem hypotenuse value. If you want to look over on our visual over here, it would be like 5, right? So I could say that the absolute value of r is just the magnitude, which is 5 meters. But if I want to express this vector r, which is the distance from this point at the beginning to the point up here at the top, then I also need to express 5 and the direction of that. Imagine you were standing here at this origin and you need to get to the other side of the triangle over here. I know I have to go 5, but I need to know the angle in order to get there, because I can't just go 5 in any direction. I have to go towards the point that I'm trying to get. And that point would be 53 degrees from the horizontal axis. So you can see here, it doesn't have to be a distance. It can be a speed or it can be an acceleration, but the magnitude, meaning the number value, is one part of the vector. And we can write that by an absolute value of this variable with the arrow over it. The direction of this, then, we have to specify. And like I said, you can use a positive sign or a negative sign if we know it's moving along a line, which would either be positive or negative, or we can have an angle if there's 2 dimensions. So this vector can be described in 2 ways, 5 meters at 53 degrees, or we can use what's called unit vector notation. So unit vector notation, really people overcomplicate this all the time, but it involves what's called unit vectors. This I with a little arrow over the top of it is called a unit vector, and it's referred to more specifically as I hat, because it's got a little hat on. And this J, which also has a little hat on, then is going to be called J hat. Now what these are they're just a vector with a value of 1. So they don't change the number when you multiply something by I hat, because if I multiply anything by 1, then the value just stays the same. So if I multiply 8 by 1, or 15 by 1, or 200,000 by 1, they don't change the value because you're just multiplying by 1. But that number 1 has a vector associated with it. So when I multiply my 8 or 15 or 200,000 by I hat, then the number value doesn't change, but you're saying that it's going to be along the positive x or the positive y axis. So for example, in our problem here, one way I can get from the beginning to the end, we said, was to go 5 meters, and that's directed at 53 degrees above the horizontal axis. The other way I can express this, which is completely fine, would be to say our vector r is going to be 3 meters horizontal, which is I hat, plus then 4 meters vertical. So you're giving essentially the rectangular coordinates, but the x and the y are going to be denoted by I hat and j hat. I already gave you a little sneak peek on this vector that we can draw here. in diagram form, so you can see here putting without numbers, we can use distances like 3, 4, and 5, or we can use velocities, or really any vector, because it can be drawn as an arrow, can be used in a right triangle. But it also can be used with these arrows you see here. These are showing the direction and the magnitude, right, with these arrows. This is an example of a force diagram, which can show the pushes and pulls that an object experiences through arrows. So we're going to use vectors a lot in a diagrammatic form. The way we draw those as labeled arrows. So the arrows are going to show us the direction. We're going to label them with your letter value and the magnitude with units. If it's applicable, meaning if they are given. Sometimes they don't give number values. They just say, we know V naught, so we'll just leave it as a variable that we know. It's like given. And scalars, as you can see, are just listed off to the side. An example of that, if we go back up to here in our diagram, t, like I just put t equals 2 seconds, or it's just listed off side, or m is equal to 5 kilograms. We could just do something like that too. Right? They're just listed off to the side. So what are the scalars and vectors we're going to see in Unit 1? There are essentially 3 different values. We have like a distance, a speed, and an acceleration. But we know that because there's scalars and vectors, we can have 2 different forms of distance and 2 different forms of speed, as we mentioned. So distance is simply how far in total. So an example here, zoom in, is if I go from point A, 10 meters, and then go back 2 meters to get to point B, then I actually end up traveling a total of 12 meters if we use the absolute value of these, right? Just total of, I put 12 miles on my pedometer, right? Now, displacement, for example, then, would be the straight line distance, because it's an arrow, that connects point A to point B. So in this case, then, you can see that point A to point B, even though I ended up going 12 meters, I really effectively only ended up 8 meters away from where I started. So that means delta x, in this case, is equal to 8 meters. And recall, delta is the triangle, and it represents change in. So it's a change in x. Since we're talking about that right now, we can look down at the note here, which would say, for example, delta x can be found by using the ending value x and the beginning value x naught. If you don't know x naught, then let's look at this right here. Putting a 0 as a subscript on a variable, like we did here with this x0 thing here, indicates that that variable is occurring at time equals 0, meaning it's the initial value of position, or if it was velocity, the initial velocity. That 0 is pronounced naught. It's a British term, which means nothing. So x naught is the way we would say the variable. So when you have your x, which is at 8, and then minus 0, right, then we would get our 8 meters. So it's just how far you end up from where you started. Speed is going to be the distance you travel, so like that 12 meters, divided by the time it took for you to travel those 12 meters, and that will give you the average speed. If you're speeding up or slowing down, remember that the distance you take and the time you take, it's going to give you the average over that entire duration. Okay, if you're speeding up or slowing down, this is not going to give you those instantaneous values. It's going to give you the average over some time interval. Velocity, on the other hand, is going to use displacement instead of distance. So velocity is a vector. We'll put an arrow over that to indicate that we know that that's going to have a direction to it. And that direction needs to be matched up, or is actually defined by the direction of the displacement. So for example, point A to point B is going to be to the right, or positive 8 meters, which means that the velocity is also going to be to the right. And that's going to be whatever the 8 meters divided by time would be. Now acceleration we'll do a lot more later, but that's going to be then the change in velocity over change in time, just like velocity is the change in your meters over seconds. This is going to be the change in your speed over the amount of time it took for you to change that speed. And this is a vector. We'll talk a lot more about that, but it does have an arrow in the way it points. Hope you enjoyed this video. There's more to come here as we go through AP Physics C. Take care.